I actually think that machine learning is not only the most exciting thing in computer science, but the most exciting thing in all of human endeavor. So you can already tell that machine learning is a highly interdisciplinary topic in which just the TAs are applying learning algorithms to problems in computer vision, in biology, in robots, in language. Machine learning is one of those things that has had and is having a large impact on many applications. Just in my own daily work, I actually frequently end up talking to people like helicopter pilots, to biologists, to people in computer systems or databases, to economists, an unending stream of people from industry coming to Stanford, interested in machine learning methods to their own problems. I think this is a good time to be learning this stuff, and learning algorithms are having a large impact on many segments of science and industry. The field of machine learning grew out of early work in AI, early work in artificial intelligence. And over the last 20 years or so, it's been viewed as a growing new capability for computers. And in particular, it turns out that there are many programs, there are many applications that you can't program by hand. To get software to fly a helicopter, have software recognize handwritten digits. One very successful approach is to use a learning algorithm and have a computer learn by itself how to, say, recognize your handwriting. And in fact, for handwritten digit recognition, this is pretty much the only approach that works well. And these are sort of applications that are hard to program by hand. Learning algorithms has also made, I guess, significant inroads in what's sometimes called database mining. So for example, with the growth of IT and computers, increasingly many hospitals are keeping around medical records of what sort of patients, what problems they had, what the prognosis was, what the outcome was. And taking all of these medical records, which started to be digitized only about maybe 15 years ago, by applying learning algorithms to the source of medical records that hospitals have just been building up over the last 15, 20 years in electronic format. Turns out that most of you probably use learning algorithms, I don't know, I think half a dozen times a day or maybe a dozen times a day or more. Every time you send mail via the US postal system, turns out there's an algorithm that tries to automatically read the zip code you wrote on your envelope, and that's done via a learning algorithm. So every time you send US mail, you're using a learning algorithm. Similarly, every time you write a check, a significant fraction of checks that you write are processed by a learning algorithm that's learned to read the digits, so the dollar amount that you wrote down on your checks. If you use a credit card, or I know at least one phone company was doing this, and lots of companies like eBay as well that do electronic transactions, there's a good chance that there's a learning algorithm in the back end trying to figure out if, say, your credit card's been stolen, or if someone's engaging in a fraudulent transaction. If you use a website like Amazon or Netflix that will often recommend books for you to buy or movies for you to rent or whatever, these are other examples of learning algorithms that have learned what sorts of things you like to buy, what sorts of movies you like to watch, and can therefore give customized recommendations to you. My car mechanic was trying to explain to me some learning algorithm and the innards of my car that's sort of doing its best to optimize my driving performance or fuel efficiency or something. It's also doing things like giving us a growing understanding of the human genome. So if someday we ever find a cure for cancer, I bet learning algorithms will have had a large role in that. Let's talk about learning algorithms. What is machine learning? Way back in about 1959, Arthur Samuel defined machine learning informally as the field of study that gives computers the ability to learn without being explicitly programmed. Arthur Samuel, so way back in the history of machine learning, actually did something very cool, which was he wrote a checkers program which would play games of checkers against itself. Because a computer can play thousands of games against itself relatively quickly, Arthur Samuel had his program play thousands of games against itself, and over time it would start to learn to recognize patterns which led to wins and patterns which led to losses. So over time it learned things like that, gee, if I get a lot of my pieces taken by the opponent, then I'm more likely to lose than win. Or gee, if I get my pieces into a certain position, then I'm especially likely to win rather than lose. At the checkers program, they would actually learn to play checkers by learning what are the board positions that tend to be associated with wins and what are the board positions that tend to be associated with losses. The amazing thing about this was that his program actually learned to play checkers much better than Arthur Samuel himself could. Right? So even today, there are some people that say, you know, well, computers can't do anything that they're not explicitly programmed to. And Arthur Samuel's checkers program was maybe the first, I think, really convincing refutation of this claim. Namely, Arthur Samuel managed to write a checkers program that could play checkers much better than he personally could. And this is an instance of maybe computers learning to do things that they really were not programmed explicitly to. Here's a more recent, or more formal definition of machine learning due to Tom Mitchell, who says that a well-posed learning problem is defined as follows. A computer program is said to learn from an experience E with respect to some task T and some performance measure P if its performance on T as measured by P improves with experience E. Right? So not only is it a definition, it even rhymes. So for example, in the case of checkers, the experience E that the program has would be the experience of playing lots of games of checkers against itself, say. The task T is the task of playing checkers, and the performance measure P will be something like the fraction of games it wins against a certain set of human opponents. And by this definition, we'll say that Arthur Samuel's checkers program has learned to play checkers. Supervised learning. So let me give you an example of that. Suppose you collect a data set of housing prices. And so what you can do is, let's say, plot the square footage of the house against the list price of the house, right? So you can, so collect data on a bunch of houses. Let's say you get a data set like this with houses of different sizes that, are listed for different amounts of money. Now, let's say that I'm trying to sell a house in the same area as Portland, Oregon, was in where the data comes from. Let's say I have a house that's, this size in square footage. And I want an algorithm to tell me about how much should I expect my house to sell for. Okay? So there are lots of ways to do this. So one thing you could do is look at this data and maybe fit a straight line to it. And then, if this is my house, you may then look at the straight line and predict that my house is going to go for about that much money, right? And there are other decisions that you can make. Well, what if I don't want to fit a straight line? Maybe I should fit a quadratic function to it. Maybe that fits the data a little bit better. You notice if you do that, the price of my house goes up a bit, so that'd be nice. And this sort of learning problem of learning to predict housing prices is an example of what's called a supervised learning problem. And the reason it's called supervised learning is because we're providing the algorithm a data set of a bunch of square footages, a bunch of housing sizes, and as well as the right answer of what the actual prices of a number of houses were. Right? And so we call this supervised learning because we're supervising the algorithm. Or in other words, we're giving the algorithm the, quote, right answer for a number of houses, and then we want the algorithm to learn the association between the inputs and the outputs and to sort of give us more of the right answers. Okay? It turns out this particular example that I drew here is an example of something called a regression problem. The term regression refers to the fact that the variable you're trying to predict is a continuous value, is a continuous valued price. There's another class of supervised learning problems which we'll talk about, which are classification problems. In a classification problem, the variable you're trying to predict is discrete rather than continuous. As one specific example that is sort of actually a standard data set you can download online that I've worked on and that lots of machine learning people have played with, let's say you collect a data set on breast cancer tumors. You want a learning algorithm to predict whether or not a certain tumor is malignant. Malignant is the opposite of benign, right? So malignant means it's a harmful, bad tumor. So we collect, some number of features, some number of properties of these tumors, and for the sake of having a simple toy explanation, let's just say that we're going to look at the size of the tumor, and depending on the size of the tumor, we'll try to figure out whether or not the tumor is malignant or benign. So tumor is either malignant or benign, and so the variable on the y-axis is either 0 or 1, and so your data set may look like that's 1 and that's 0. Okay? And so this is an example of a classification problem where the variable you're trying to predict is discrete values, either 0 or 1. In fact, more generally, there'll be many learning problems that have more than one input variable, more than one input feature, and use more than one variable to try to predict, say, whether a tumor is malignant or benign. So for example, continuing with this you may instead have a data set that looks like this. I'm going to plot this data set in a slightly different way now. And I'm making this data set look much cleaner than it really is in reality, where maybe the crosses indicate malignant tumors and the O's may indicate benign tumors. And so you may have a data set, patients of different ages and who have different tumor sizes, and where a cross indicates a malignant tumor and an O indicates a benign tumor. And you may want an algorithm to learn to predict, given a new patient, whether their tumor is malignant or benign. Right? So for example, what a learning algorithm may do is maybe come in and decide that a straight line like that separates the two classes of tumors really well. And so if you have a new patient whose age and tumor size fall over there, then the algorithm may predict that the tumor is benign rather than malignant. Okay? So this is just another example of another supervised learning problem and another classification problem. And so it turns out that one of the issues to talk about later in this class is, in this specific example, we're going to try to predict whether a tumor is malignant or benign based on two features, or based on two inputs, namely the age of the patient and the tumor size. Turns out that when you look at the real data sets, you find that learning algorithms often use other sets of features. In the breast cancer data example, you also use properties of the tumors like clump thickness, uniformity of cell size, uniformity of cell shape, marginal adhesion, and so on. So various other medical properties. And one of the most interesting things we'll talk about later this quarter is what if your data doesn't lie in a two-dimensional or three-dimensional or sort of even a finite dimensional space? But is it possible, what if your data actually lies in an infinite dimensional space? Right? I plotted here a two-dimensional space. And so it turns out that one of the most successful classes of machine learning algorithms, something called support vector machines, maps data to an infinite dimensional space and then does classification using not two features like I've done here, but an infinite number of features. It's actually an interesting question, right? So think about how do you even represent an infinite dimensional vector in computer memory? You don't have an infinite amount of computers. How do you even represent a point that lies in an infinite dimensional space? So that was supervised learning. The second of the four major topics of this class will be learning theory. In this class, I'm going to talk about learning theory to try to convey to you an understanding of how and why learning algorithms work, so that we can apply these learning algorithms as effectively as possible. It turns out you can prove surprisingly deep theorems on when you can guarantee that a learning algorithm will work. Right? So think about a learning algorithm for reading zip codes. When can you prove a theorem guaranteeing that a learning algorithm will be at least 99.9% accurate on reading zip codes? This is actually somewhat surprising. We actually prove theorems showing when you can expect that to hold. We'll also sort of delve into learning theory to try to understand what algorithms can approximate different functions well and when, and also try to understand things like how much training data do you need? So how many examples of houses do I need in order for your learning algorithm to recognize the pattern between the square footage of a house and its housing prices? And this is help us answer questions like, if you're trying to design a learning algorithm, should you be spending more time collecting more data, or is it the case that you already have enough data and it'd be a waste of time to try to collect more? Okay, I think learning algorithms are a very powerful tool, but as I walk around industry in Silicon Valley, or as I work with various students in CS and outside CS, you find that there's often a huge difference between how well someone who really understands this stuff can apply a learning algorithm versus someone who sort of gets it but sort of doesn't. One thing that's sadly not taught in many courses on machine learning is how to take the tools of machine learning and really apply them well. Large parts of this class will be just giving you the raw tools of machine learning, just the algorithms and so on. But what I plan to do throughout this entire quarter, not just in the segment of learning theory, but actually as a theme running through everything I do this quarter, will be to try to convey to you the skills to really take the learning algorithm ideas and really to get them to work on the problem. When I walk around companies in Silicon Valley, it's completely not uncommon for me to see someone using some machine learning algorithm and then explain to me what they've been doing for the last 6 months, and I go, oh, gee, it should have been obvious from the start that the last 6 months you've been wasting your time, right? And so my goal in this class, running through the entire quarter, not just on learning theory, is actually not only to give you the tools of machine learning, but to teach you how to use them well. And I've noticed this is something that really not many other classes teach. This is something I'm really convinced is a huge deal. And so after learning theory, there's another class of learning algorithms that I then want to teach you about. And that's unsupervised learning. A little earlier, I drew an example like this, right, where you have a couple of features, a couple of input variables, and sort of malignant tumors and benign tumors or whatever. And that was an example of a supervised learning problem because the data you have gives you the right answer for each of your patients. The data tells you this patient has a malignant tumor, this patient has a benign tumor. So it had the right answers, and you wanted the algorithm to just produce more of the same. In contrast, in an unsupervised learning problem, this is the sort of data you get, where, speaking loosely, you're given a data set, and I'm not going to tell you what the right answer is on any of your data. I'm just going to give you a data set, and I'm going to say, would you please find interesting structure in this data for me? So that's the unsupervised learning problem, where you're sort of not given the right answer for everything. So for example, an algorithm may find structure in the data in the form of the data being partitioned into two clusters. So clustering would be one example of an unsupervised learning problem. These sorts of unsupervised learning algorithms are also used for many problems. This is a screenshot, this is a picture I got from Sue and Lee, who's applying unsupervised learning algorithms to try to understand gene data. Look at genes in individuals and group them into clusters based on properties of what genes they respond to, based on properties of how the genes respond to different experiments. Another interesting application of these sorts of clustering algorithms is actually the image processing. This picture I got from Steve Gould, who's another PhD student. It turns out what you can do is if you give this sort of data, say an image, to certain unsupervised learning algorithms, they will then learn to group pixels together and say, gee, this set of pixels seem to belong together and that set of pixels seem to belong together. So the images you see on the bottom are groupings, are what the algorithm has done to group different pixels together. This sort of clustering algorithm, this sort of unsupervised learning algorithm, which learns to group pixels together, it turns out to be useful for many applications in vision, in computer vision image processing. Let's show you one example. This is a rather cool one, which is given an image like this. You can apply that sort of clustering algorithm and group the picture into regions. So in the middle, you see the lines sort of grouping the image together, grouping the image into contiguous regions. And what Ashutosh and Min did was they then applied the learning algorithm to say, can we take this clustering and use it to build a model, to build a 3D model of the world? And so, using the clustering, they then had a learning algorithm try to learn what the 3D structure of the world looks like so that they could come up with a 3D model that you can sort of fly through. Okay. By the way, many people used to think it's not possible to take a single image and build a 3D model. But using a learning algorithm and that sort of clustering algorithm as the first step, they were able to. I'll just show you one more example. I like this because it's a picture of Stanford, of our beautiful Stanford campus. So again, taking the same sort of clustering algorithms, you can, taking the same sort of unsupervised learning algorithm, you can group the pixels into different regions. And using that as a pre-processing step, eventually built this sort of 3D model of Stanford campus from a single picture. So you can sort of walk into the scene, look around the campus. This actually turned out to be a mix of supervised and unsupervised learning, but the unsupervised learning, the sort of clustering, was the first step. These sorts of unsupervised clustering algorithms are actually routinely used for many different tasks. Things like organizing computing clusters, social network analysis, market segmentation. So if you're a marketer and you want to divide your market into different segments or different groups of people to market to them separately. Even for astronomical data analysis and understanding how galaxies are formed. These are just a sort of small sample of the applications of unsupervised learning algorithms, of clustering algorithms. Just one particularly cool example of an unsupervised learning algorithm that I want to tell you about. So it's what's called the cocktail party problem. Right? Imagine that you're at some cocktail party and there are lots of people standing all over. And you know how it is, right? If you're at a large party, and everyone's talking, it can be sometimes very hard to hear even the person in front of you. So imagine a large cocktail party, lots of people. So the problem is, if there are all of these people talking, can you separate out the voice of just the person you're interested in talking to, right? Because with all this loud background noise. So I show you a specific example in a second. But here's a cocktail party that's, I guess, rather sparsely attended by just 2 people. And what we're going to do is we'll put 2 microphones in the room. Because the microphones are just at slightly different distances to the 2 people, and the 2 people will be speaking at slightly different volumes. Each microphone will pick up an overlapping combination of these 2 people's voices, but they are sort of slightly different overlapping voices. So speaker 1's voice may be more loud on microphone 1, and speaker 2's voice may be louder on microphone 2, whatever. But the question is, given these microphone recordings, can you separate out the original speaker's voices? So this is the microphone 1.
1, 2, 3, 4, 5, 6, 7, 8, 9, y 10.
So it's a fascinating cocktail party with people counting from 1 to 10. This is the second microphone.
1, 2, 3, 4, 5, 6, 7, 8, 9, y 10.
Remember, in unsupervised learning, we don't know what the right answer is, right? So what we're going to do is take exactly the 2 microphone recordings you just heard, and give it to an unsupervised learning algorithm and tell the algorithm, would you please discover structure in the data for me? Or what structure is there in this data? When we actually don't know what the right answer is offhand. So give this data to an unsupervised learning algorithm. And what the algorithm does in this case, it'll discover that this data can actually be explained by 2 independent speakers speaking at the same time. And it can further separate out the 2 speakers for you. So here's output 1 of the algorithm.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
And that was the second output.
1, 2, 3, 4, 5, 6, 7, 8, 9, y 10.
Okay, and so the algorithm discovers that, gee, the structure underlying the data is really that there are 2 sources of sound, and here they are. Show you one more example. This is a different pair of microphone recordings.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
So the poor guy is now at the cocktail party where he's talking to his radio.
1, 2, 3,
There's a second recording.
5, 6, 7, 8, 9, 10.
Right, and if you give this data to the same unsupervised learning algorithm, the algorithm is actually called independent component analysis, and later in this quarter you'll see why. It then outputs the following.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
And that's the second output. Okay, so it turns out that beyond solving the cocktail party problem, this specific class of unsupervised learning algorithms are also applied to a bunch of other problems, like in text processing or understanding functional brain imaging data, like magnetoencephalography and EEG data. And as an aside, this algorithm I just showed you, right, it seems like it must be a pretty complicated algorithm, right? To take these overlapping audio streams and separate them out. It sounds like a pretty complicated thing to do. So you're going to ask, how complicated is it really to implement an algorithm like this? Well, it turns out, if you do it in MATLAB, you can do it in 1 line of code. If you try to implement the same algorithm in C or Java or something, you end up writing pages of code rather than relatively few lines of code. I should mention that it did take researchers, many, many years to come up with that 1 line of code. So this is not easy. That was unsupervised learning. And then the last of the 4 major topics I want to tell you about is reinforcement learning. And this refers to problems where you don't do one-shot decision making, right? So for example, in the supervised learning cancer prediction problem, you have a patient come in, you predict that the cancer is malignant or benign, and then based on your prediction, maybe the patient lives or dies, and then that's it. You make a decision, and then there's a consequence. You either got it right or wrong. In reinforcement learning problems, you are usually asked to make a sequence of decisions over time. So for example, this is something that my students and I work on. If I give you the keys to an autonomous helicopter, how do you write a program to make it fly? Right? You notice that if you make a wrong decision on a helicopter, the consequence of crashing it may not happen until much later. And in fact, usually you need to make a whole sequence of bad decisions to crash a helicopter. But conversely, you also need to make a whole sequence of good decisions in order to fly a helicopter really well. Let me show you some fun videos of learning algorithms flying helicopters. This is a video of our helicopter at Stanford flying using a controller that was learned using a reinforcement learning algorithm. So this was done on the Stanford football field. We'll zoom out the camera in a second. You sort of see the trees planted in the sky. So this is one of the most difficult aerobatic maneuvers flown on any helicopter under computer control. And this controller, which is very, very hard for a human to sit down and write out, was learned using one of these reinforcement learning algorithms. The basic idea behind the reinforcement learning algorithm is this idea of what's called a reward function. One way to think about it is, imagine you're trying to train a dog. So every time your dog does something good, you say, you know, good dog, and you reward the dog. Every time your dog does something bad, you go, bad dog. Right? And hopefully over time, your dog will, you know, learn to do the right things to get more of the positive rewards, to get more of the good dogs, and to get fewer of the bad dogs. So the way we teach helicopter to fly, or any of these robots, is sort of the same thing. Every time the helicopter crashes, we go bad helicopter. And every time it does the right thing, we go good helicopter. And over time, it learns how to control itself so as to get more of these positive rewards. So reinforcement learning I think of it as a way for you to specify what you want done. So you have to specify what is a good dog and what is a bad dog behavior. And then it's up to the learning algorithm to figure out how to maximize the good dog reward signals and minimize the bad dog punishment. Reinforcement learning is applied to other problems in robotics, it's applied to things in web crawling and so on, but it's just cool to show videos. This learning algorithm was actually implemented by our head TA, Zico, programming a four-legged dog, because Sam Schreiber in this class is also working on the project, and Peter Rebu and Mike and a few others. Second video on the right, some of the students, Peter, Zico, Tonka, working on a robotic snake, again using learning algorithms to teach a snake robot to climb over obstacles. Low left, this is a kind of fun example. Arshad Saxena and Jeff Michaels use learning algorithms to teach a car how to drive at reasonably high speeds off-road, avoiding obstacles. On the lower right, there's a robot programmed by PhD student Yirong Shen to teach sort of somewhat strangely configured robot how to get on top of an obstacle, how to get over an obstacle. So I think all of these are robots that I think are very difficult to hand code a controller for, but using these sorts of learning algorithms, you can, in relatively short order, get a robot to do, often pretty amazing things. That was most of what I wanted to say today. I'll see you in a couple of days.